In this video, we are going to begin to review and do some practice problems for our first midterm. So that's our one goal for this day's videos. And because that's a really short goal to state, I want to just dive right into doing some practice problems rather than making a separate video purely for the overview. Okay, so let's begin by reviewing hyperbolic functions and doing an example. Alrighty, so the example is evaluate the following integral. If it involves inverse hyperbolic functions, then rewrite it in terms of logarithms. So at this point, I want you all to try the problem. So pause the video for about 2 minutes, maybe 3 minutes, 2 minutes, 2 to 3 minutes. So 4, 3, 2, 1, pause the video. Pause the video and try this problem for about 2 to 3 minutes. That's likely not going to be enough time to finish the question, but I want you to practice how you would begin and what the key steps are to getting started. So really seize this time to try this problem, especially as you're practicing for an exam in math. It's really important to practice solving new questions, because that's the type of thing that you'll be asked to do on a quiz or an exam, solve new questions. So that's why it's really important today, especially, to be pausing the video and actually be trying these questions. All right, so hopefully you've done that. Hopefully you've paused the video for about 2 to 3 minutes to try this. If not, go ahead and do so now. Okay, so let's talk about this. All right, so looking at this, there are 2 ways we could go about this. So the first way, method 1, is this integral looks familiar with an integral that we've seen before. In fact, we know that the integral of, if you have 1 on the top, and I can put dx with that, and then square root of x squared minus 1 in the denominator, that is hyperbolic cosine inverse of x. And then I put a plus c because this is an indefinite integral, so I need to put a plus c there. So method 1 is to use inverse hyperbolic functions. So on our exam, I'm going to give you a list of the derivatives of all of the inverse hyperbolic functions. So if you notice that you have an integral problem and the integral that you're trying to take matches the form of one of these inverse hyperbolic functions derivatives, that's a tip-off that we might want to do it that way. Okay, so, well, how do we use that? So we want to begin by getting our integral to match this form exactly, so I can use this formula. Okay, so to do that, what we would need is, instead of having a 10 here, we need to have a 1. So I need to factor a 10 out of that square root. So for right now, let me just put it inside the square root, and I have a 10, but just factoring out. And then I'll get 4x squared over 10 minus 1. On the top, I still have dx. So I got this fraction. All right, so now we can take that 10 all the way out in front, and it'll become 1 over square root of 10. And then I have dx on top. And on the denominator, I really want to write this first term as something squared. So it matches up with the fact that I have something squared over here. Okay, so, and then we have the minus 1 after that. All right, well, so what squared equals 4x squared over 10? Well, it's going to be a 2x in the numerator, and it's going to be a root 10 in the denominator. Okay, so now I'd really like for this whole squared term to become like a u squared. Because if it becomes a u squared, I'm going to get to use this formula that involves whose integral becomes this inverse hyperbolic cosine. So that's telling me that I probably want to do u substitution at this point. Let's do u substitution and let u equal 2x over root 10. And then writing du would be 2 over root 10 dx. And if I isolate for the dx, we get root 10 over 2 du equals dx. All right, so let's plug this stuff into our integral. So what do we have? We have 1 over root 10 in front. Integral, the dx in the numerator becomes root 10 over 2 du. And in the denominator, we have square root of u squared minus 1. All right. So now this root 10 over 2, we can pull that out to the front. And doing that, the root 10s will cancel. So the root 10s will cancel, and we will end up with a 1/2 in front. Integral of du over square root of u squared minus 1. And now this matches the form. This matches the form of this integral that we had here. All right, so now this gives us 1/2 times hyperbolic cosine inverse, except my variable is a u here. So u, and then I have to put a plus c because it's an indefinite integral. Okay, so I got this hyperbolic cosine inverse. That's good. The question said, whenever I have inverse hyperbolic functions, I need to rewrite them in terms of logs. So I'm going to provide you on the midterm all of the formulas that let us rewrite the inverse hyperbolic functions in terms of logarithms. So the formula for cosine inverse is cosine inverse becomes ln u plus square root of u squared minus 1. That's a formula I'll provide for you on the exam. So hyperbolic cosine inverse is equal to this when we rewrite it in terms of logs. Okay, and then we have the plus c. But remember, my original integral was in terms of the variable x. And I need to get it back in terms of x. So let's plug back in for what u is. So we get 1/2 ln, plugging in for u. U is 2x over root 10 plus, then I'll have u squared, and if I square u, we would get 4x squared over 10 minus 1 plus c, and that is our answer right there. So that is our answer. Okay, so what's the other way that we could do this? Okay, so what is method 2? Okay, so one thing that we've seen before when we talked about hyperbolic functions was I talked about a tip-off when I see an integral about something that I can look for that would indicate I'm going to use method 2. So if I see something like the square root of something minus x squared, or the square root of something plus x squared, if I see something like that, I might want to try trig sub. Might want to try trig sub. And the reason why I say might is if there's a different technique that I could use that would be easier, like u sub or something, I'd want to do it that way. Okay, so for example, if I had something like x over square root of 5 minus x squared, even though I see a term that looks like square root of something minus x squared, this is really nice. Oh, and I should write dx. This is really nice for u sub. So for something like this, u sub is best. It's best because if we let u equal 5 minus x squared, I see a multiple of du in our problem. Du would be negative 2x. Okay, I need a little bit more room. Negative 2x dx. And I see a multiple of that in the numerator. Okay, so u sub would be great there. But for our problem, we don't see something like that with our integral. So trig sub is probably going to be a good way to go. So let's also talk about how to do this using trig sub. Okay, so how do we do this using trig sub? So remember, we have the integral dx, I'm just going to recopy it, square root of 4x squared minus 10. All right, so when we do trig sub, what I first want to do is I want to draw a right triangle. So a right triangle. And I want to make one of these other acute angles theta. And it doesn't really matter which one. So I'll make that one on the left. Okay, and then if we see something like square root of something minus x squared, we want to make this the leg of our right triangle. But if we see something like the square root of something plus x squared, we want to make this the hypotenuse. Assuming that this stuff here is a positive number. Okay, so in my problem, I see, actually maybe it would be better for me to generally say, if in my square root, if I see one thing that's positive and one thing that's negative, that's a good idea to make it a leg. But if I see both of the things are positive, then I should make that thing my hypotenuse. So in this case, I'm going to make this square root term a leg, and it doesn't matter which leg I make it. So let me just put it over here. So square root of 4x squared minus 10. And then the way I figure out those other side lengths is I do some Pythagorean theorem, and then form a good guess for what the a and the c would be. So using Pythagorean theorem, we would get a squared, I'm just going to put a blank parentheses there for it, plus b squared. So b squared would just give me 4x squared minus 10. It would get rid of that square root. That's going to be equal to c squared. So a squared plus b squared equals c squared. Let's just put a blank parentheses there. C squared. So now, to make this work out really nicely, I'd like this first parentheses squared to be 10, so that the positive 10 cancels this negative 10. And then that would mean that the second parentheses squared would be 4x squared. Okay, so of course that means that a, the thing that goes inside of this parentheses, would be the square root of 10. And the thing that would go inside the second parentheses would be the square root of 4x squared, which is 2x. I don't need to worry about positives or negatives because the lengths of my triangle are going to be non-negative. All right, so now I want to set up some trig functions using this triangle for the quantities that I see in my problem. So I need some trig function that will involve this square root, and I want to pick a trig function that won't involve a side length, that won't involve a side length that has another variable. So although tangent will involve the square root, it'll also involve the 2x, and the 2x has a variable in it. So it's better to pick, I meant to say sine. Sine would not be a good choice, because sine involves the square root length as well as the 2x length, so that's not great. But tangent would be better, because tangent would give me that square root, 4x squared minus 10, and then divided by root 10, and the thing on the denominator doesn't have a variable, which is good. Okay, and then if I isolate for that square root, we get root 10 times tangent theta equals the square root of 4x squared minus 10. All right, but I'm going to need something that's going to give me a dx as well, so I can switch the dx to a d theta. So it's best to choose a trig function that's as simple as possible to take the derivative of. So taking the derivative of the square root isn't the nicest thing that I could have. So the simplest trig function that I could have in terms of what the derivative would be is secant. If we did secant of theta is 2x over root 10. And then having this x in the numerator in particular is really nice in terms of what the derivative would be. So now if we take the derivative both sides, we'd get secant theta, tangent theta, d theta on the left. And on the right, that derivative would be 2 over root 10, because that's the constant multiplying the x, and we'd have dx. Okay, so now let us go ahead and substitute this stuff into our integral. So if we do that, we end up getting the integral. So what's dx going to be? Well, if we move this 2 over square root of 10 to the other side, we'd get root 10 over 2 secant theta, tangent theta, d theta in the numerator. On the denominator, we have that square root, which we now know is square root of 10 times tangent theta. And then we could simplify this because the tangents cancel. So let me continue this at the top of the page to give myself some more room. All right, so, and also the square root of 10 cancels, so that square root of 10 cancels this one on the bottom. And we end up getting, we can move the 1/2 in front of the integral. And we have 1/2 integral of secant theta d theta, and we've seen the integral of secant before. This is one that we might have to look up to remember if we don't quite remember it, but we've seen this a number of times now in the videos and in the homework. This is ln absolute value secant theta plus tangent theta. And then indefinite integral, so I put a plus c. I can't stop here because remember, my original integral was in terms of x, not theta. So I have to plug back and get it in terms of x. So I use my triangle for that. And my triangle, I can see that secant of theta is going to be 2x over square root of 10. And tangent of theta is going to be square root of 4x squared minus 10 over square root of 10. So in fact, I can actually make that one big square root. One big square root and put the 10 underneath. Because both the numerator and the denominator have a square root. Oops, ln, cool. And that is our answer. Okay, so if we compare this to what we got doing it the first way, we actually have the same thing. If we got a common denominator with the minus 1 and the 4x squared over 10, it's actually the same thing. One subtle difference that you might notice is, wait, in the answer that we just got, there's an absolute value. Technically, we can actually get rid of the absolute value in this specific example because the inside of this absolute value ends up being positive. But that's not a detail that I'm going to stress. So it'd be fine to leave it as it is.